A over x dp, and that's what you wanted, isn't it? Yeah, yeah. So we started from here.
Yes, sir.
Okay. And we ended up here. Is it making sense?
So when we are taking A is equals to union of K equal to 1 to 2.
Because the definition of sigma field generated by y is equal to the sigma field generated by the collection of all such sets. Okay? And then I could be in,
But sir, we don't know that A belongs to all of them or some of them.
I'm sorry.
We don't know whether A belongs to all of them or some of them.
So I can do one thing. Here's the thing. A contains omegas,
Yes, sir.
and those omegas are in somewhere here actually.
Yes, sir.
Okay? All of those omegas are somewhere in these.
So that's why we've chosen subsequent seconds.
Yes, that's what essentially I'm saying. So take the omegas, okay, which are in A, because this is the subset of capital omega, sample space. So these omegas must be in one of these actually. Now here's an interesting thing. How many are these things? So these are countable.
Yes, sir.
Okay. So in other words, the outputs, the elements of A are in these countable guys actually.
Yes, sir.
So I don't know precisely which of these guys, okay, but there are some guys which contains these basically all things. So therefore you're going to say that yes, A is
A is union or A is contained in the union of
but the other way around is also true. Why not? Think about it. You know, other way around is also true. That's true by default. Think about it. So, okay. If a sigma field is generated by countably many sets,
Yes, sir.
then any element of that set can be written as, so you can prove a separate result actually,
Yes, sir.
as the union of, countable union of, those basis sets actually, which are generating.
So we can assume that.
Okay. Let's move ahead. Let's now define. By the way, as I said, this property that you proved here is a very particular case of it by just taking A to be omega. So in other words, these two properties are the crucial properties. Okay. Now we're going to sort of like to point out to a pretty interesting thing in mathematics that we do all the time. So you have a particular notion. Okay? any notion, any mathematical notion that satisfies some properties. For example, I took conditional expectation and it satisfies, for example, these two properties. Now I want to generalize this particular notion. And I don't know the definition, how to define that general thing. So what I'm going to say, anything that satisfies such a property would be the generalization of this given notion actually. So in other words, generalizing by known properties. Is it making sense what I'm saying? So I'm saying that conditional expectation of x given y, where x is integrable random variable and y is a discrete random variable, okay, is a particular case in the sense that y is discrete actually. X can be anything but y is discrete, okay, and so it must satisfy these two properties. Now here's the thing, I want to replace discrete y by any y. How can I define it? The answer is, I have a no explicit definition for this, but I know conditional expectation of arbitrary x given arbitrary y, whatever it is going to be a random variable. If it is generalizing this conditional expectation, it must satisfy these two properties actually. Okay? So for conditional expectation x given y discrete, you have an explicit formula to calculate probabilities. But for conditional expectation x given y, we don't have an explicit formula. You have to always construct this random variable actually. Are you getting the point? But these properties must be there. So you define it. Now keep this thing, well, that's a philosophical point actually in mathematics. So sometimes you want to generalize a thing, okay, particular notion, but you don't know that how to generically describe it. So you're going to say, okay, anything in general that satisfies these two properties is the generalization of this notion. That's it. So, okay, and that's how we're going to define. And you will see in mathematics quite often this coming up actually, that okay, you want to generalize a notion. So what you do, you say that okay, that general thing must satisfy those properties which are present in a particular case. Okay? So conditioning on an arbitrary. So it's not. So this comment was not in the context of this, notion. So it was a general comment. You will see it actually someday. I know that maybe some of you got it and some of you didn't, but you're gonna find it. So one day I was saying arbitrary random variable. Let's write this, do one example, and then we can do break. Then we're going to do the most general case. That's it. That would be the last theorem for us. So let's do definition and one example, one simple, very simple example. Okay. Here's the definition. We say that let x be integrable random variable and y be an arbitrary random variable. Even there is no condition of integrability yet. So I'm not even, because like this y is more general than this x actually, because x must be integrable. While y, you can take absolutely anything. You can make it weaker, but okay, we can make it weaker. There are notions. But taking this absolutely away, I think this would be difficult. Okay. Maybe there are ways, but I don't know. Then the conditional expectation of x given y from omega, I'm going to treat this as a map from omega into R, is a random variable. It's a random variable that satisfies the properties that I just wrote previously. Number one, that this conditional expectation x given y must be sigma of y measurable.
Expectation of expectation is expectation.
And the second thing, it must be that for any a in sigma of y, okay, if you compute the integral of the conditional expectation of x given y over a with respect to dt, then it must be equal to x dt. So any random variable that just satisfies these two properties, we're going to term it as conditional expectation. Now, this definition is a very troublemaking definition. Think of it, doesn't give you an explicit formula. It just tells you, okay, anyone who has this property, okay, is the conditional expectation. Now, अपने ढूंढ चला अगर वो खुज़े वाले का ना. So you can ask the first question: does such random variable exist? Okay, why? In other words, for any given x and y, where x is integrable and y is random, is it necessary that we can always find such a random variable? Number one. Second, is it necessary that it must be unique? So if we can prove it that yes, for each such x and y, such a random variable always exists and it must be unique, then this definition is a well-defined definition. Otherwise, no. Okay? This is what I like. So are you really tired?